When we look at the night sky, we see a billion destinations. For decades, humanity has aimed to reach them, imagining a future where we finally leave our solar system behind. But any plan for deep space travel immediately collides with a problem of scale. The universe is not just big, it is efficiently, crushingly empty. Take Alpha Centauri, our closest neighbor. It sits 4 light-years away. Even light, the fastest thing in existence, requires 4 years to make that trip. If we sent our fastest current spacecraft today, the crew wouldn't arrive for tens of thousands of years. For all practical purposes, the stars are out of reach. Conventional rockets can only take us so far. To reach another star within a single human lifetime, we need a way to move that doesn't involve simple propulsion. The primary obstacle is a rule established by Albert Einstein. His special theory of relativity sets a hard speed limit for everything in the universe. Einstein discovered that mass and energy are linked. As you push an object to go faster, you have to add energy. But that energy itself adds effective mass to the object, making it harder to accelerate even further. This chart shows the mathematical result. As a ship nears the speed of light, the energy required to go any faster shoots toward infinity. Because infinite energy is not available, no object with mass can ever travel through space faster than light. It is a physical wall that cannot be breached by better engineering. While nothing can travel through space faster than light, the rules say nothing about how fast space itself can move. Space is not an empty void. It is a flexible fabric that can be bent. In 1994, physicist Miguel Alcubierre proposed a way to exploit this. It's called the Alcubierre warp drive, and it functions by changing the geometry of the universe around a ship. The drive would work by contracting space in front of the vessel, effectively shortening the distance the ship needs to cross. Simultaneously, it would be expanding space behind the ship, pushing it forward. The spacecraft sits in the middle of this distortion, a warp bubble. Inside this bubble, space remains flat and the ship stays stationary. Because the ship isn't moving through its local space, it never hits Einstein's infinite energy wall. The bubble moves the ship, allowing it to arrive at a destination faster than light would, without ever actually breaking the speed limit. We know that space can expand faster than light because we see it happening at the edges of the observable universe. Distant galaxies are moving away from us at superluminal speeds. They aren't traveling through the void between us is physically stretching. To recreate this effect in the lab, however, we need something called negative energy. To expand or contract space on command, you need matter with properties that are the opposite of everything we see in the daily world. While quantum effects like the Casimir effect show that tiny amounts of negative energy exist, we have no known way to harvest or concentrate enough of it to fuel a spacecraft. Even if we found a source of negative energy, we would then face a power requirement that defies modern engineering. Original calculations suggested that to move a small ship, you'd need an energy amount equal to the mass of an entire galaxy. But physicists refined the math. By changing the bubble's shape, the requirement was drastically reduced. But reduced is a relative term. Current estimates suggest you would still need to convert the entire mass of the planet Jupiter into pure energy just to make the drive work. We aren't just missing a better engine, we are missing a way to harness the energy output of a planet. Even with infinite power, the physics of the journey itself might be catastrophic. As a warp bubble moves, it would act like a cosmic vacuum, sweeping up high-energy particles and trapping them in a concentrated wall of radiation at the front of the bubble. When the ship reaches its destination and the bubble collapses, that concentrated radiation would be released forward in a massive, lethal burst. Anything at the destination, be it a planet or a colony, would be obliterated. Because of these energy and safety barriers, the warp drive remains a mathematical concept, not an engineering project. No one is building a prototype, because we lack the physics to even begin. The Alcubierre model doesn't promise a starship, but it proves the universe's geometry is far more malleable than we once believed. It shows that while our current technology is grounded, the mathematical laws of the universe haven't completely closed the path to the stars.